Number 1, the unexplained sub-Pacific mantle structures. In November of 2024, a doctoral student named Thomas L. A. Schouten at ETH Zurich's Geological Institute published a finding that unsettled deep Earth science. Beneath the western Pacific Ocean, between 900 and 1200 kilometers below the surface, his team detected a massive anomaly. Something is down there that, according to our current understanding of plate tectonics, should not be. The technique that found it is called full waveform inversion. Traditional seismology picks apart individual wave types from earthquake recordings. Full waveform inversion analyzes entire seismograms, extracting far more information from the same data. The model Schouten's team used is called REVEAL, developed by Thrastarson, Van Herwarden, Neuer, Schiller, and Fichtner. Published in the Bulletin of the Seismological Society of America in 2024, running REVEAL required the Piz-Dane supercomputer in Lugano, Switzerland, one of the most powerful computing systems in the world. The sheer volume of global seismic data demanded that kind of processing power. What REVEAL showed was a set of high-velocity zones. Seismic waves pass through them faster than through surrounding material. In geophysics, that typically means the rock is either colder or compositionally different from its neighbors. These zones sit in the middle third of Earth's mantle, which extends 2,890 kilometers from crust to core. They are below the transition zone at roughly 660 kilometers, but well above the core mantle boundary. Here is the problem. The Pacific Plate is the largest tectonic plate on Earth. It is a single continuous plate. Subduction happens only at its edges. There are no subduction zones in the interior of the Pacific Plate, and there haven't been in recent geological history. So there should be no subducted slab material sitting beneath it at that depth. Professor Andreas Fichtner, Schouten's supervisor, compared it to a doctor suddenly seeing an artery where anatomy textbooks say one cannot exist simply because the imaging tool got better. Statistical analysis confirmed that these anomalies do not correlate with any known past subduction zones. That breaks a foundational assumption. For decades, geophysicists assumed that high-velocity zones in the mantle always represented recycled plate material, old ocean floor that sank at a subduction trench and settled at depth. Four previous tomography models, UU-P07, GAP-P4, SEMU-CB-WM1, and GLAD-M25, either missed these features entirely or rendered them as vague smears at lower resolution. Three competing explanations are now on the table. The mainstream theory says these are ancient subducted slab fragments that somehow migrated laterally over hundreds of millions of years from distant subduction zones. That requires material to drift sideways through the mantle over enormous distances, which is plausible but poorly constrained. The second theory is geological and much older in implication. These could be primordial silica-rich pockets from early mantle formation, roughly 4 billion years old, that survived billions of years of convection without being mixed in. If that is true, it challenges every existing convection model, because convection should homogenize the mantle over that time scale. The third theory is more speculative. These could be iron-rich accumulations representing a completely unknown class of mantle heterogeneity, not predicted by any existing model. Schouten himself urges caution. They are interpreting deep structure using just one property of waves: speed. That single parameter cannot determine actual composition. Future research will need to combine P-wave speed, S-wave speed, and density measurements simultaneously to narrow down what these anomalies actually are. But the implication is already significant. The mantle is far more compositionally varied than plate tectonics predicts. It is not simply a hot churning mass. It contains distinct features, geological fossils that have persisted for potentially billions of years. If trapped cold material exists at these depths, it affects heat flow patterns and could influence surface volcanism and plate motions. Some researchers have compared this discovery's potential impact on deep Earth science to what the discovery of the mid-ocean ridge system did for surface geology in the 1960s. The ocean hides structures that break our models. That pattern is going to repeat. And the next one starts much closer to the surface, on the continental shelf where ancient rivers are still flowing. Number 2, Wonky Holes, the ghost rivers of the continental shelf. Off the coast of Australia, commercial fishers have long known about spots on the continental shelf where fish congregate in unusual density. The water temperature shifts slightly. The salinity drops. Something is leaking fresh water into the ocean from below. Australians call these spots wonky holes. The technical term is submarine groundwater discharge points. They are locations where ancient buried river channels sealed under coral and marine sediment still push fresh water into the sea. The rivers themselves last flowed across exposed land during the last glacial maximum, roughly 20,000 years ago, when sea levels were approximately 120 meters lower than today. As ice melted and seas rose, the river valleys drowned. Marine sediment and coral buried them. But the underground aquifer connections were never severed. The underlying geology is a sandwich. Quaternary sediments, laid down over the last 2.6 million years, form the permeable middle layer. Holocene marine deposits, much younger, sit on top. Fresh water still flows through that middle layer and finds its way out at the seafloor. The scale of this process globally is staggering. Total submarine groundwater discharge integrated over the Atlantic and Indo-Pacific Oceans is estimated at 120,000 cubic kilometers per year. That is 3 to 4 times greater than the fresh water delivered by all the world's rivers combined. Most of this is recirculated seawater, but it becomes enriched during its passage through coastal aquifers. It picks up trace elements, rare earth elements, nutrients, and dissolved carbon. Fish aggregate at Wonky Holes because the discharge carries dissolved iron, nitrogen, phosphorus, and silica from terrestrial aquifers. These nutrients are scarce in open ocean water. The salinity anomalies at the seafloor can be detected by conductivity sensors but are invisible from above. Australian examples cluster along the Great Barrier Reef Shelf and the Southeast Australian margin, where quaternary alluvial deposits from ancient rivers create permeable conduits. Most Wonky Holes remain unmapped. Discovery is often anecdotal, reported by fishers who noticed something unusual, and told a scientist. Geologist Niels Moosdorf of the Leibniz Center for Tropical Marine Research in Bremen, Germany, has noted that science simply had not given submarine springs much thought. In 2017, Moosdorf and colleague Till Oehler published a paper in Earth Science Reviews documenting societal use of submarine freshwater discharge as an overlooked resource. In Japan, oysters from aquaculture thrive particularly well near submarine freshwater springs. The mainstream theory treats these as straightforward hydrogeological continuity. Glacial-era rivers left permeable sediment channels that passively persist under modern marine cover. A historical theory goes further. Ancient coastal peoples may have known about and exploited these features for millennia. Oral traditions describing sweet water in the sea appear across Pacific and Indian Ocean cultures. The speculative theory is the most provocative. Some researchers believe the volume of offshore freshwater is so vast it represents an untapped global resource. Massive trapped aquifers beneath continental shelves may contain more freshwater than all water ever extracted from land-based wells. These features face real threats. Land-based well drilling reduces the hydraulic head that drives discharge. Agricultural runoff pollutes the flow. Sea level rise alters the pressure gradients. Their ecological role may be vastly underestimated. They could be critical, yet invisible drivers of productivity across continental shelves worldwide. But Wonky Holes are just one expression of something leaking through the ocean floor. The next formation involves something far more solid being exposed where it should not be. Raw mantle rock sitting on the seafloor without any volcanic activity to explain it. Number 3, the Godzilla Megamullion. In the Paresse Vela Basin of the Philippine Sea, roughly 600 kilometers southeast of Japan's southernmost coral reef, sits the largest oceanic core complex on Earth. It is approximately 155 kilometers long and 55 kilometers wide. Ridges within it reach 2,500 meters above the surrounding seafloor. Its name is the Godzilla Megamullion. Marine geologist Yasuhiko Ohara and colleagues from the Japan Coast Guard's Hydrographic and Oceanographic Department first reported it after a 2001 survey. In February of 2023, the Japan Coast Guard announced that the name had been officially approved at an international conference organized by the International Hydrographic Organization and UNESCO. Its 14 individual ridges are named after Godzilla's body parts: Hat Ridge, Head Peak, West Shoulder Ridge, Neck Peak, East Shoulder Ridge, and others. Toho's chief Godzilla officer, Keiji Ota, called it an honor. It is believed to be the first geological feature named after a fictional character. To understand why the Godzilla Megamullion matters, you need to understand how it formed. At mid-ocean ridges, tectonic plates pull apart and magma rises to fill the gap, creating new oceanic crust. That is the standard process. But at slow-spreading ridges where magma supply is limited, faults can penetrate deep enough to reach mantle rock directly. Instead of lava building new crust, the fault mechanically pulls mantle rock up to the seafloor. This is called an oceanic core complex. The structures are dome-shaped, extending 15 to 30 kilometers in diameter, with conspicuous corrugations called mullions running parallel to the direction of fault slip. The faults involved are low-angle detachment faults. As the complex builds, seawater penetrates the fault and reacts with mantle peridotite, producing serpentinite and talc. These minerals act as lubricants, allowing the fault to continue slipping for over 1 million years. Rocks recovered from the Godzilla Megamullion include peridotites, gabbros, diabase, and serpentinites. They provide a natural cross-section through the entire oceanic lithosphere. The Paracevela Basin formed by back arc spreading as the Philippine Sea Plate evolved eastward. The Godzilla Megamullion likely formed during the final stages of this spreading, around 12 to 15 million years ago. Only about 50 oceanic core complexes have been identified worldwide. The Godzilla Megamullion dwarfs all of them, over 10 times larger in area than typical examples on the mid-Atlantic ridge. The serpentinization process also produces hydrogen gas and methane without any biological input. These chemicals fuel microbial ecosystems independent of sunlight, making oceanic core complexes directly relevant to astrobiology. The mainstream view treats the Godzilla Megamullion as an extreme but well-understood end member of detachment faulting at magma-starved spreading centers. A geological alternative suggests its formation during the final stages of back arc spreading may represent something fundamentally different, a dying spreading center's last act, not replicable under normal mid-ocean ridge conditions. The speculative theory is broader. Structures this large may indicate that the textbook model of oceanic crust, the neat layering of sediment, then basalt, then gabbro, then mantle, is not the rule, but potentially the exception across large portions of slow-spreading ocean floor worldwide. The textbook version may be the anomaly. At oceanic core complexes, that layering is absent or inverted. And they are not the only places where something unexpected erupts from the seafloor. The next formation involves volcanoes that erupt not at lava, but tar. Number 4. Asphalt volcanoes. In 2003, researchers exploring the Gulf of Mexico found something on a seafloor hill named Chapopote, a Nahuatl word meaning tar. At depths between 2,900 and 3,150 meters, they encountered dome-like mounds made entirely of heavy, solidified petroleum. No magma, no lava, volcanoes that erupt asphalt. In 2007, David Valentine led a team that discovered 7 more structures off Santa Barbara, California. The largest dome, called Il Duomo, sits at 213 meters depth. It stands 20 meters tall and contains an estimated 50,000 cubic meters of crude oil. Off Angola, side-scan sonar has identified over 2,254 asphalt mounds covering 3.7 square kilometers of seafloor, roughly the area of a small town. Carbon dating places the California structures at 30,000 to 40,000 years old. They may account for a mysterious spike in oceanic methane concentrations around 35,000 years ago. The extruded hydrocarbons are predominantly heavy, biodegraded oils with API gravity values near or below 10 degrees, enriched in asphaltenes and resins, dense enough to approach the weight of seawater itself. The textures are strikingly similar to basaltic lava. Blocky forms resembling and smooth, ropey forms resembling pehoho appear across these mounds. The shapes are produced not by heat but by viscosity gradients as volatile components escape the petroleum. When scientists cracked open 35,000-year-old asphalt from the seafloor, it still smelled like a gas station. Oil compounds remained unweathered despite millennia underwater. Woods Hole scientists described diving on Il Duomo in the submersible Alvin as encountering a black wall of tar covered in diverse life. The Angolan mounds host at least 21 types of deep-water creatures, including large sponges, soft corals, octopus, blobfish, and sea cucumbers. Chemosynthetic communities thrive. Albinocaris shrimp, iceworms, and mussel beds colonize the flows, fueled by methane and hydrogen sulfide seeping through the tar. Some Gulf of Mexico structures have split into shapes resembling palm lily fronds, earning the nickname tar lilies. These volcanoes erupt in tectonically slow motion, building successive layers over decades or centuries. Fossil organisms are entombed in the oil. Plankton shells within the asphalt allowed radiocarbon dating of the eruptions. The mainstream theory places these within standard petroleum geology. Hydrocarbon migration through salt diapirs or compressional tectonics creates natural seep systems. Asphalt volcanoes are extreme versions of common cold seeps. The historical theory considers the methane burst from the eruptions around 35,000 years ago. That pulse may have fueled methane-eating bacteria, reduced local oxygen levels, and created dead zones, potentially correlating with paleoclimate shifts visible in ice cores. The speculative theory goes wider. If asphalt volcanoes are far more numerous than currently mapped, they could represent a significant unaccounted source of natural hydrocarbon input into the oceans, complicating climate models that assume most marine hydrocarbons come from human activity. Unlike true volcanoes, asphalt volcanoes have a single petroleum source and limited exit points. They eventually die as the reservoir depletes. And Mexico's ultra-deep offshore energy leases overlap directly with extensive asphalt pavements and gas hydrate mounds, making them an active drilling hazard. The asphalt volcanoes preserve hydrocarbon material that migrated from deep within the earth. The next formation preserves something even older, a piece of ocean floor that got stuck halfway through the planet 250 million years ago. Number 5. The fossil seafloor trapped in Earth's mantle. In September of 2024, postdoctoral researcher Jingchuan Wang at the University of Maryland, working with professors Vedran Lekic and Nicholas Schmer, published a finding in Science Advances. Using advanced seismic imaging, they detected an anomalous structure in the Mantle transition zone, the region between roughly 410 and 660 kilometers below the surface. Wang described it as a fossilized fingerprint of an ancient piece of seafloor that subducted into the Earth approximately 250 million years ago. That timing places it in the late Permian and early Triassic, the age of the Great Dying, Earth's largest mass extinction, and the supercontinent Pangaea. The slab apparently got stuck. Its unusual thickness suggests colder material persisting in the transition zone. Some oceanic slabs, rather than sinking continuously to the core mantle boundary, stall partway down. The location makes it doubly surprising. It was found at the East Pacific Rise, a mid-ocean ridge where plates are currently spreading apart. This is an area associated with the creation of new seafloor, not the destruction of old slabs. Wang compared the imaging technique to a CT scan, providing a cross-sectional view of the planet's interior. The mantle transition zone is bounded by two-phase transitions. At 410 kilometers, the mineral olivine transforms into wadsleyite. At 660 kilometers, ringwoodite converts to bridgemanite and ferropericlase. The density contrast at the 660-kilometer boundary can trap descending slabs. That is a known phenomenon. But what makes this finding significant is its preservation. Usually, oceanic slabs are consumed completely, leaving no discernible trace. This one survived as a geological fossil. The team believes the slab may explain the anomalous structure of the Pacific Large Low Shear Velocity Province, one of two continent-sized superplumes in Earth's lower mantle. The LLSVP appears to be split by the slab, suggesting these massive deep structures are not permanent fixtures, but are actively shaped by ongoing subduction. A critical finding: the material was moving through the mantle at about half the expected speed. The mainstream view holds that slab stagnation at the 660-kilometer discontinuity is well documented, and this is simply a particularly well-preserved example. The geological alternative argues that the slab's interaction with the Pacific LLSYVP means superplumes are dynamic features, not stable ones, rewriting our understanding of the deepest mantle. The speculative theory considers scale. If stalled slabs are widespread, they could collectively contain enough sequestered carbon to significantly alter estimates of Earth's deep carbon budget, with implications for volcanic carbon dioxide output models going back billions of years. The techniques used here could eventually be applied to Mars and Venus, which may have had ancient subduction processes. But for now, we return to the surface, to a formation whose bottom has never been reached. Number 6. The Taam Blue Hole. At the southeast corner of Mexico's Yucatan Peninsula in Chetumal Bay, there is an underwater sinkhole called Taam. The name means deep water in the Mayan language. Around 2003, a local diver named Jesus Artemio Potville followed a grouper into its mouth. Then the hole was largely forgotten until his son began working with marine researcher Juan Carlos Alcerica Huerta. The depth measurements tell the story of its rediscovery. The initial 2016 survey measured 275 meters. A 2023 survey found 900 feet. Then, in December of 2023, a CTD profiler, which measures conductivity, temperature, and depth, was lowered past 420 meters with no bottom detected. That makes Taam the deepest known blue hole on Earth, surpassing the previous record holder, the Sanchayongal Blue Hole in the South China Sea, by at least 120 meters. The mouth is nearly circular, with a major axis of 151.8 meters, aligned with major faults in the area. Water properties below 400 meters did not resemble the bay above. They resembled the Caribbean Sea and nearby coastal reef lagoons. That suggests hidden subterranean connections to the open ocean through cave networks. The CTD profiler detected several Pycnock lines, thin bands where water density shifts quickly, indicating a strongly stratified water column with layers that may remain isolated for long periods. The hole sits in rock-rich in gypsum and evaporite minerals. Water becomes saltier and sulfate-heavy at depth through mineral dissolution. Divers explored the top 30 meters. Walls were not uniform. Some surfaces were soft and fragile, coated in biofilms. Deeper walls appeared steeper and firmer. Blue holes formed during past ice ages when low sea levels exposed limestone to rainwater and chemical weathering, dissolving rock and creating vertical cave systems. When seas rose, they flooded. The Yucatan Peninsula's limestone is extremely porous, containing an estimated 10,000 cenotes and one of the world's largest underground freshwater systems. The mainstream theory treats Taam as standard karst dissolution, an exceptionally deep but mechanically ordinary sinkhole formed by Pleistocene rainfall over hundreds of thousands of years. The geological alternative emphasizes its fault alignment and subterranean ocean connections. Taam may be part of a vast regional karst network, a three-dimensional underground system far larger than the single visible opening implies. The speculative theory focuses on temperature and salinity anomalies at depth. Combined with the fact that no bottom has been reached, these raise the possibility that Taam connects to deep geological structures, perhaps geothermally active zones that could host extremophile ecosystems cut off from the surface entirely. NASA's astrobiology program has described blue holes in the Bahamas as testbeds for exploring how life might persist in dark, layered water bodies beyond Earth, environments analogous to icy moons like Europa. The study was published in Frontiers in Marine Science in April of 2024, led by Alcerica Huerta of Sur in Chetumal, Mexico. Future exploration requires autonomous underwater vehicles and deep-rated remotely operated vehicles. For now, Taam is deeper than 1,390 feet. Its deepest point is unconfirmed, and it may extend well beyond what current technology can reach. Blue holes preserve layered, isolated water columns. The next formation sits at the opposite extreme, under Arctic ice, where the ocean floor does something that physics says it cannot do: explode. Number 7. The Gakkel Ridge Pyroclastic Fields. The Gakkel Ridge is the slowest spreading mid-ocean ridge on Earth. It extends roughly 1,800 kilometers beneath the Arctic Ocean, from north of Greenland to Siberia. Its plates pull apart at rates as low as 6 to 11 millimeters per year. Before 2007, the prevailing view was that volcanism at ultra-slow ridges would be entirely effusive, gentle lava flows, and nothing more. The Gakkel Ridge disproved that. In 2007, the Arctic Gakkel Vents Expedition, known as AGAV, discovered large deposits of pyroclastic material on the seafloor, glass-like volcanic fragments scattered over areas comparable to small towns. The glass shard layers were several centimeters thick. The deposits had been flung up to 10 or more kilometers from vent sites. That dispersal distance implies blast energies far exceeding anything expected at these depths. The physics problem is fundamental. At depths exceeding 3,000 meters, hydrostatic pressure should prevent water from boiling. Explosive eruptions on land depend on gas expansion and steam flashing. Neither should be possible under a 3-kilometer water column. The Gakkel Ridge sits at depths between 3,000 and 5,500 meters, among the deepest mid-ocean ridge segments anywhere, and it is covered by permanent Arctic sea ice. The material consists primarily of sideromelane shards, fragments of quenched basaltic melt identical to products of explosive eruptions on land. The discovery was published in Nature in 2008 by Robert Sohn of the Woods Hole Oceanographic Institution and colleagues. They had first detected eruption signals via seismoacoustic monitoring back in 1999, when a swarm of over 200 earthquakes occurred in a short period, the largest known volcanic episode detected teleseismically on any mid-ocean ridge at that time. The proposed mechanism centers on volatile accumulation. At ultra-slow spreading ridges, magma collects in isolated chambers for long periods, building up carbon dioxide and other volatile concentrations far beyond what faster ridges produce. When this volatile enriched magma finally breaches the seafloor, dissolved carbon dioxide exsolves so violently it fragments the melt even under extreme hydrostatic pressure. This is volatile-driven fragmentation. Hydrothermal vents discovered on the Gakkel Ridge host up to 100,000 times higher density of organisms than the surrounding ocean. Because the vents are so isolated, they likely harbor species found nowhere else. Underwater robots found mats of microbial life growing directly on the pyroclastic deposits. Hydrogen produced by serpentinization of mantle rock along the ridge fuels these microbial ecosystems entirely independent of sunlight. The mainstream interpretation accepts volatile-driven fragmentation as a well-understood mechanism that simply had never been observed at this depth. The historical theory focuses on biology. The extreme isolation means species at Gakkel vents must have either evolved in place over millions of years or arrived through extremely long-distance larval dispersal. Both scenarios are poorly understood, suggesting these ecosystems may be far more ancient and self-sustaining than anyone assumed. The speculative theory considers climate change. As Arctic ice retreats, thinning ice could alter pressure and thermal dynamics affecting the ridge's volcanic activity, potentially increasing eruption frequency in ways not accounted for in current models. The Gakkel Ridge's ultra-slow spreading means new oceanic crust forms at roughly the rate your fingernails grow, yet it still produces violent explosions. Serpentinization keeps appearing. It showed up at the Godzilla Megamullion, and it is here again. It is going to appear a third time. But first, the freshwater phenomenon from Australia needs to be widened into its global context. Number 8. Submarine freshwater springs. The first scientific study of submarine groundwater discharge was published by Sonrel in 1868. He speculated about risks the phenomenon might pose to sailors. Then, the field was largely ignored for over a century until the mid-1990s. The history of human interaction with these springs goes back much further. In 15th century Bahrain, divers filled goatskin bags with fresh drinking water collected from the Persian Gulf seabed. In Bali, the Hindu sea temple Tanah Lot was built on a submarine freshwater spring. 2 million people make pilgrimage there annually. In Peru, submarine spring water is pumped into trucks for national distribution. In Greece, it irrigates fields. One spring off Florida provides roughly 40 cubic meters of fresh water per second, equivalent to a medium-sized river. The global scale is enormous. Submarine groundwater discharge accounts for up to 10% of water carried into the sea through rivers by some estimates, and much more when recirculated seawater is included. Subsea freshwater pools have been found thousands of miles apart: Tanzania, Indonesia, New Jersey, and New England. During 1970s, drilling 60 miles off the New Jersey coast, an artesian spring erupted from a borehole. The New England offshore freshwater likely originated from Ice Age glaciers depositing meltwater and porous rock that later became seafloor as sea levels rose. Moore's 1996 study in the South Atlantic Bight off South Carolina was the first regional-scale investigation. He used radium-226 as a groundwater tracer, measuring enhanced concentrations up to 100 kilometers from shore. Georgian hydrogeologists have reported submarine springs at 5 to 7 meters depth near Tsandripsh, 25 to 30 meters near Gagra, and discharge at depths up to 400 meters near the Arabaka Massif. A historical connection worth noting: the crew of the Essex, The whale ship whose destruction inspired Herman Melville's Moby Dick survived partly because of submarine groundwater discharge providing drinkable water. Freshwater discharges can carry 10 times as many nutrients as river water, making submarine groundwater discharge potentially a primary nutrient pathway for coastal oceans. Offshore freshened groundwater can extend up to 90 kilometers from the coast. Total nutrient fluxes from submarine discharge may be comparable to global riverine nutrient export and of the same magnitude as global nitrogen fixation rates. That makes this a planetary scale process. The mainstream theory treats it as well understood hydrogeology driven by terrestrial hydraulic head. The historical perspective is striking. Musdorf has noted that in ancient Greece, horses were sacrificed to Poseidon at submarine springs near Argos. Civilizations have recognized these features for millennia, and traditional knowledge networks may map more springs than modern science currently documents. The speculative theory is economic. In the 1990s, Florida explored tapping submarine groundwater for Miami's drinking water supply. Offshore freshwater mining could become a major industry, though the ecological consequences of depleting these aquifers remain completely unstudied. Sea level rise will alter the hydraulic gradients driving discharge, potentially reducing flow rates, shifting discharge locations, and cascading through dependent coastal ecosystems. What seems like a hidden geological curiosity may in fact be infrastructure that entire marine food webs depend on. And speaking of hidden layers with outsized consequences, the next formation is the most visually dramatic of all. It is an underwater river flowing inside a cave, complete with banks, currents, and a toxic cloud separating two entirely different ecosystems. Number 9. Cenote, Angelita's underwater river. Near the ancient Mayan city of Tulum, on the east coast of Mexico's Yucatan Peninsula, there is a cenote called Angelita. The name means little angel in Spanish. It is approximately 60 meters deep. The first 29 meters are clear freshwater. Below that, salt water. And between them, something that looks like it should not exist. A river, flowing inside the ocean, with visible banks, currents, and a thick cloud of mist. The river is not water of a different kind. It is a hydrogen sulfide. At the halocline, the boundary where saltwater meets freshwater, organic matter accumulates. Leaves, branches, fallen trees, debris trapped at the density interface. This material decomposes, producing hydrogen sulfide gas, which is heavier than salt water. The gas becomes trapped in a thick cloud-like layer between the two water masses. Freshwater floats above, dense saltwater sits below. The hydrogen sulfide hangs between them. The physics is straightforward density stratification, the same principle that separates oil and vinegar. But the visual result is extraordinary. The accumulated debris forms convincing riverbanks. The halocline layer moves through the cenote with visible flow and current. Photographer Anatoly Boloshchin's images of divers appearing to hover above a misty flowing river inside the ocean became some of the most shared underwater photographs ever taken. Two distinct ecosystems exist in the same cenote, separated by a toxic boundary. The upper freshwater layer contains more oxygen and supports different life forms than the saltwater below. Divers passing through the hydrogen sulfide cloud report tingling lips and fingers, blurred vision, disorientation, and a strong sulfurous stench. The halocline also traps human pollution. Plastic bags, soda cans, and other trash collect at the density boundary, unable to sink into the denser layer below. Cenote formation across the Yucatan follows a consistent pattern. The peninsula is composed primarily of porous limestone. Over thousands of years, rainwater dissolved rock and formed vast underground river systems. The Yucatan has an estimated 10,000 cenotes, many interconnected by the world's longest known underwater cave systems. Sistema Sac Octun has been mapped at over 376 kilometers. Halocline depth varies, 10 to 20 meters below the water table at the coast, 50 to 100 meters in the peninsula's interior. The ancient Maya considered cenotes sacred portals to Xibalba, the underworld. Human remains and sacrificial artifacts dating back thousands of years have been recovered. In 2001 and 2002, expeditions led by Arturo H. Gonzalez discovered 3 human skeletons in Yucatan cenotes. One specimen, called Eve of Naharon, was carbon dated to 13,600 years old. The mainstream interpretation treats Angelita as an especially photogenic example of halocline chemistry, well documented in stratified water bodies worldwide. The historical perspective is broader. The Cenote system functions as the Yucatan's primary freshwater aquifer. The peninsula has almost no surface rivers. Cenotes are the sole perennial water source for millions. The Maya civilization's rise and fall may have been intimately linked to access to these systems. The speculative theory considers biology. Similar halocline effects at other cenotes, the Pit, Taj Mahal, Chakmul, suggest a vast interconnected toxic boundary ecosystem stretching across the peninsula, potentially hosting undiscovered extremophile organisms adapted to hydrogen sulfide environments. The ongoing Maya train construction threatens cenotes directly. The railway cuts through karst terrain, risking collapse or contamination of the underground aquifer system connecting them. A modern infrastructure project potentially destroying formations that took hundreds of thousands of years to develop. From an underwater river in a limestone cave, we move to the final formation. This one takes every theme so far, mantle exposure, serpentinization, tectonic stress, and pushes them to their logical extreme, a place where Earth's deep interior stands above the ocean's surface. Number 10. The St. Peter and St. Paul Rocks. In the equatorial Atlantic Ocean, roughly equidistant between Brazil and West Africa, a tiny cluster of bare rock islets rises just 18 meters above sea level. Total emergent land area is about 15,000 square meters, roughly 4 acres. They sit atop an oceanic core complex 90 kilometers long and 4,000 meters tall. These are the St. Peter and St. Paul rocks, and they are composed of peridotite, ultramafic mantle rock, not basalt, not volcanic rock. That makes them fundamentally different from virtually every other oceanic island on Earth. Hawaii, Iceland, the Azores, all formed from magma rising through the crust. The St. Peter and St. Paul rocks were tectonically squeezed upward. Cold, solid mantle rock forced above sea level by fault mechanics. They sit on the St. Peter and St. Paul Massif at the intersection of the Mid-Atlantic Ridge and the St. Paul Transform Fault, a major fracture zone. Transform faults create inside corners where tectonic stresses exhume deep rock along low-angle detachment faults, the same mechanism that built the Godzilla Megamullion, pushed here above the waterline. Charles Darwin visited aboard HMS Beagle in 1832. He noted their unusual non-volcanic composition. That is one of the earliest scientifically documented examples of exposed mantle rock, though the mantle origin was only confirmed by modern petrology much later. The peridotite is heavily serpentinized. Seawater reacted with olivine and pyroxene minerals, converting them to serpentine group minerals and releasing hydrogen gas. This is the same chemical reaction that appeared at the Godzilla Megamullion and the Gakkel Ridge. At all three locations, serpentinization produces abiotic methane and hydrogen, chemicals that sustain microbial life without sunlight. 3 separate formations, 3 oceans, 1 reaction. Brazil maintains a permanently staffed scientific research station on the rocks, established in 1998, with rotating researchers and military personnel. The geopolitical significance is real. The rocks define part of Brazil's exclusive economic zone. The station was established partly to assert sovereignty over surrounding waters. The islets have no soil, no vegetation, no permanent freshwater. Raw, bare mantle rock polished by waves and colonized only by algae, barnacles, and crabs. Surrounding deep waters host a unique pelagic ecosystem. The rocks serve as a mid-Atlantic waypoint for migratory seabirds, brown boobies, and noddies, one of very few available land points in the open ocean. Similar exposed mantle exists at Zabergad Island in the Red Sea and at the Atlantis Massif on the Mid-Atlantic Ridge, but none are as dramatically oceanic or as isolated as the St. Peter and St. Paul rocks. And because there is no volcanic activity replenishing them, the rocks are slowly eroding by wave action. Their above-water existence is geologically temporary. The mainstream theory sees standard oceanic core complex formation at a ridge-transform intersection. Well-understood tectonic mechanics produce an unusually prominent example, and the rocks' position above sea level is a fortunate geometric accident. The historical perspective points to Darwin's documentation and centuries of navigator reports. These barren rocks have been recognized as anomalous for at least 500 years, yet their mantle origin was only confirmed recently. How many other anomalous oceanic features remain unexamined? The speculative theory considers the massif's scale. 4,000 meters of height, active serpentinization, and a composition that produces hydrogen and methane suggests a vast, never-surveyed chemosynthetic ecosystem could exist on and within the massif itself. Studies of the serpentinized peridotite reveal mantle flow patterns, melt migration, and deformation history millions of years in the making. It is a geological core sample brought to the surface for free, a window into the mantle that, by all geological logic, should remain sealed kilometers underground. Every formation in this documentary preserves something that should have been destroyed. 4-billion-year-old mantle pockets, a 250-million-year-old slab, 20,000-year-old river channels, 35,000-year-old tar. The ocean floor is the least explored surface on Earth. More of the Moon and Mars have been mapped at high resolution than the deep seafloor. Each discovery came from a specific technological advance: full waveform inversion seismology, CTD profilers, the submersible Alvin, side-scan sonar, underwater robotics, radium tracers. And in every case, the initial discovery was accidental or incidental. Fishers finding wonky holes. A diver following a grouper. Seismologists noticing unexpected signals. The formations span every depth, from 30-meter cenote surfaces to 3,000-meter pyroclastic fields, to 660-kilometer deep fossil slabs to 1,200-kilometer mantle anomalies. They span every timescale, from freshwater discharge happening today to structures 4 billion years old. The ocean resists homogenization at every scale: chemical layers in cenotes, thermal layers in blue holes, compositional layers in the mantle. Serpentinization appeared in 3 separate sections: the Godzilla Megamullion, the Gakkel Ridge, the St. Peter and St. Paul rocks. It is a single planetary scale process. Olivine plus water yields serpentine plus hydrogen. That reaction lubricates faults, raises mantle rock above sea level, and fuels ecosystems that have never seen sunlight. Every chemosynthetic ecosystem found on Earth strengthens the case for life on Europa, Enceladus, and other ocean worlds. NASA has cited blue holes as analogs for layered water bodies on icy moons. The Gakkel Ridge's microbial ecosystems, functioning entirely without photosynthesis, are the baseline model for how life could persist beneath Europa's ice shell. Volatile-driven fragmentation at extreme pressures is relevant to cryovolcanism models for Enceladus. Abiotic methane production via serpentinization is now a leading hypothesis for methane detected in Mars's atmosphere by the Curiosity rover and ESA's Trace Gas Orbiter. Several formations face direct threats from human activity. Cenote contamination from the Maya train. Aquifer depletion drying up Wonky Holes. Offshore drilling near Asphalt Volcanoes. Climate-driven Arctic ice loss potentially altering Gakkel Ridge dynamics. The economic stakes are real. Massive offshore freshwater aquifers. Mineral deposits at oceanic core complexes. Fisheries dependent on submarine groundwater discharge nutrients. Drilling hazards from unmapped asphalt pavements. Natural hydrogen production from serpentinization. Japanese oyster farms already benefiting from submarine springs. Cenote diving generating tens of millions in annual tourism revenue. Brazil staffing a military research station on bare mantle rocks to secure an exclusive economic zone. The resource frontier is real. But exploitation without understanding risks destroying formations before we know what they are. Every formation discussed was found in the last 25 years, most in the last decade. The pace of discovery is accelerating. Better sensors, cheaper computing, more autonomous underwater vehicles. Yet funding for ocean science remains a fraction of space exploration budgets. There's a pattern in every section. A better instrument reveals a formation that no model predicted. The formation forces a model revision. The revision predicts new features. Those features require still better instruments. That cycle has no natural stopping point. Every formation obeys the same physics taught in introductory geology: pressure gradients, density stratification, chemical equilibria, tectonic stress fields. Nothing here requires new physics. The hydrogen sulfide river in Cenote, Angelita is just density stratification. Serpentinization follows the same reaction at 3 locations and produces 3 different outcomes. Asphalt volcanoes create textures identical to basaltic lava because viscosity physics does not care whether the fluid is molten rock or cold petroleum. Explosive volcanism at 3,000 meters follows the same volatile exsolution mechanics as surface eruptions. Blue holes are standard karst dissolution. The fossil slab stalled at a well-known phase transition boundary. Freshwater flowing beneath the ocean obeys the same hydraulic principles as every well and spring on land. The fundamental laws are simple. The forms they produce are not. Billions of years of unobserved operation in the largest, least accessible environment on Earth produced formations that break every simplified model we built from limited observation. The creativity is not ours. It belongs to the system, operating patiently under constraints we can describe, but whose consequences we have barely begun to count. Every formation discussed was found within the last 25 years, most in the last decade. The next decade will reveal formations we cannot currently imagine, produced by the same laws operating in conditions we have not yet measured. The ocean floor is full of structures that should not exist. Every one of them does. Somewhere beneath the Western Pacific, seismic waves are passing through an anomaly that no model predicted. It is still there. It is still unexplained.